Okay, so we were talking last time about section 13.2. 13.2 deals with line integrals. And we learned about the line integral uh, with respect to arc length. I want to say it the right way. I want to use the exact way the book says it. So the line integral with respect to arc length of a function along a curve C, a space curve C, is given by that third formula. And we actually derived that formula. But we also learned that you can find line integrals of a function along a curve C, a space curve C, with respect to the variable x and with respect to the variable y. Okay, and those definitions, hold on, here we go. Well, we actually showed those as well. Those are the two formulas for line integrals with respect to variable x and with respect to variable y. So these line integrals ultimately have tremendous applications, and you're going to see that today. But I want to do a problem that deals with line integrals. Let me just hold on here. I want to do a problem that deals with line integrals with respect to x and y, with respect to those variables. So let me bring up a file here. We did in our last class a problem dealing with finding the center of mass of a wire with a certain linear density. So and that was an application of the line integral with respect to arc length formula. Now let's look at another problem, a problem like this. This is a problem where we want to evaluate this line integral right here. But remember, that line integral is really the sum of two line integrals. One with respect to x, the variable x, and the other with respect to the variable y. Okay, so it's notation. So this problem requires us to find two line integrals and add them. And in this problem, there are two little problems. Okay, so the curve C, we have a curve C1, which is a line segment that goes from the coordinate -5, 3 to 0, 2. And then part B, we have a different arc that's a parabola that goes from the same beginning point, -5, -3, to the point 0, 2. Let me let you copy this down, okay? Okay, so again, we are finding the sum of two line integrals, and the beginning, and we're finding the sum of two line integrals, this sum, across two different paths. The paths both start at -5, -3, that coordinate, and they end at 0, 2. Okay, but they're different paths. So let's go ahead and work the problem out. So first thing I do is I draw a picture. I draw a picture here. Let's focus on the first space curve because that's the line segment. That goes from -5, 3 to 0, 2. Now, you can draw a picture of that. Well, I want to say it the right way. One moment. I mean, how would you parameterize this 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 line segment? Well, remember I had mentioned in the last class that there's a special formula that can be used. It's formula 8, okay, and it's exclusively for a line segment. So anytime you have a line segment, you can find the parametric equations of the line segment using this vector equation. 1 minus t times an initial point r sub 0 plus t times the end point. So 1 minus t times r sub 0. R sub 0 is your beginning point of the line segment. Plus t times r sub 1. R sub 1 is the end point of the line segment. And t, the limits on the parameter t is between 0 and 1. Between 0 and 1. Always, if you use this formula. And that's what's nice, because you don't have to worry about what the limits are on your parameter t. If you use that formula 8, t is between 0 and 1. So the initial point had coordinates -5, 3. That's r sub 0. And the end point is 0, 2. That's r sub 1. So the vector, the space curve, the parametric equations for the space curve turn out to have coordinates, x coordinate -5 plus 5t, and a y coordinate y equals 5t minus 3, where t goes from 0 to 1. Are there any questions on that? All right. Let me give you a moment to catch up here. Now, we'll talk about the second space curve, C2, in a moment. Okay, so now what we need to do is we need to find then the sum of the two line integrals, one with respect to x and one with respect to y. Now, I guess while I'm at it, you know, the second curve, what about the second curve? Well, the second curve, let me just see here. No, I'll go back to that. Give me a thumbs up if you're okay so far. Okay, Christopher's good, Matthew's good, Alexander's good, Narina's good, Samuel's good. Wonderful, wonderful. Okay, so our goal now, and we'll come back to the second space curve, our goal is to compute the sum of these two line integrals, one with respect to x and one with respect to y. Let's go to the next page. All right, now, of course, these line integrals with respect to x and y, we can, the line integral, because of the parameterization, the x and y coordinates are functions, as you know, of time. So to compute the line integrals, we need to integrate with respect to the variable t. Well, let's look at the first line integral here with respect to dx. If x is -5 plus 5t, then dx dt is equal to 5. And so dx is 5 dt. So the 5 dt you can replace for the dx, right? This here is dx, right? And of course, the t limits go from 0 to 1. Similarly, for the second line integral, when you integrate with respect to y, well, y is equal to 5t minus 3. Well, dy dt is 5, so dy is 5 dt. And so 5 dt is what you're going to put in here, right? Because that equals dy. This is the kind of work I'm going to want to see on your fourth exam, right? These kind of steps. You can't just, get to this step without doing this work, right? All right. So now it's basically a calculus 1 problem. We have to find these two integrals, and the first integral has a 5t minus 3 squared here. So I FOIL that out. That's 5t minus 3 times 5t minus 3. That'll get you 25t squared minus 2. Well, maybe I should say plus 2 times -3 times 5t plus -3 squared. And that's going to get you 25t squared minus 30t plus 9. Second integral is no problem. You do your antiderivatives, and you should get -5/6 when you're done. And actually, this example that we're doing corresponds to example 4 in the textbook in section 13.2. All right, so I'll let you copy. Please let me know if you have any questions. Okay, so you get negative 5, 6. And that is the value of the sum of the line integrals over the first curve. Now that's part A. Now part B says, okay, find the sum of the line integrals over the second curve. Well, if we go back here to the picture, so the second curve is the paraboloid given by x equals 4 minus y squared. Okay, that's the paraboloid. And you could go into Desmos and easily graph that. And it starts at, that starts at negative 5, 3 and ends at 0, 2 as well. We're limiting the curve to that beginning and starting point. Beginning point, starting point. So how do you parameterize this? Well, it's probably easiest to let y equals t, then x is 4 minus t squared. And if you do that, boom, you have your parameterization. Now t is between negative 3 and positive 2. Okay, why would that be? Well, let's look at 0, 2. So, you know, when is x equal to 0 here? Well, if x is 0, then 0 would, you know, by the parameterization for x, 0 would equal 4 minus t squared. And so t would equal, well, t could equal plus or minus 2, but I'm going to let t equals 2. The reason being is that the starting point here at negative 5, negative 3, if we, you know, take negative 5, which is the x coordinate, and set it equal to the 4 minus t squared, you're going to get negative 9 equals negative t squared. So 9 is t squared. Okay, and so t could be plus or minus 3, but the curve, as you move along the curve, as you move along this curve here, this C2 curve, t is increasing. So let t start at negative 3, okay, for this point here, and then the beginning point of that parabola. And then for the end point, let t equal +2. I mean, it's fine. It's fine. It really won't work the other way because you can't, if you can't go from t equals 3, like t equal, well, I want to say this the right way. Let me see here. Oh, well, hold on. You know, I'm making this too hard. I'm making this too hard. Hold on, let me, I made this too hard, class. Let's look at this space curve C2 again. Here it is, the parabola. Look here, for there, y equals t, right? So here's y equals -3. So t is -3. That's at the beginning point. And then the end point is 0, 2. Y equals 2, so t equals 2. Much easier. The other one's kind of confusing. That locks it down. Okay, and again, that space curve you could draw in Desmos. So now you have the parameterization for C2. So now let's go to that one. Let's go to that one. So for part B, you're adding up the two line integrals, and the C2 curve here, x is 4 minus t squared. So dx dt is -2t. So dx is -2t dt. Similarly, remember, y equals t, so dy is dt. And so again, you know, for dx here, dx is -2t dt. Okay, and for dy, we replace dy with dt. And of course, the t limits are from 2 to -3. Okay, and then you just work it out. You work it out. And let me let you copy here. So I'm putting in the kind of work I would want you to show on the exam. Not too hard, right? Please let me know if you have any questions. Okay, so let's go to the next page then, if you're good, and we'll finish this. The line integral, the sum of the line integrals, it turns out to equal 40 and 5/6. Now there's something interesting here about this problem. When we found the sum of the line integrals, along that first space curve, which was the line segment connecting that started at the point -5, -3, and ended at the point 0, 2, that was equal to -5/6. But when we added the same two line integrals, but did those line integrals with respect to the second curve, which was the parabola, sideways parabola that began also at the point -5, -3, and ended also at the point 0, 2. We ended getting a different answer. We got 40 and 5/6. Okay, we got a different answer, right? So this means then that in fact this vector field is not a conservative. Well, I want to say this the right way. If we had a conservative vector field, the sum of those line integrals, that you would get the same answer. But of course, okay, well, you're probably wondering, well, where's the vector field, Dr. Duty? I don't see a vector field. I don't see a vector field in this problem. Well, that's true. That's true. The vector field in this problem is actually this vector field. First component is the y² here, and which is the component of, now hold on here. I want to have a dx here, right? That should be a dx, right? First component's the y² that goes with the dx. The second component of the vector field is the x. So basically, the way you could interpret this, and I'm actually jumping ahead of myself, but you see, as you know, a vector field in space, whether it's a two-dimensional or space or three-dimensional space, the vector field represents either velocity flow, fluid flow, force field flow. So think of the vector field as a force field, and the force field as a particle moves along a space curve from a beginning point to an end point, the force field either helps or hinders the particle from moving from the beginning point to the end point. So if we imagined the particle moving along, well, so, and of course the different paths that the part, if you have like any 2 points and you have different paths, okay, to go from one point to the other, the normal thinking is that, well, okay, since you're moving along different paths from a beginning point to an end point, the work that the force field does in helping move the particle from the beginning point A, say, to an ending point B, and that work could be positive or negative, depending on whether the force field's helping or hindering the movement. you would think you would think that that the uh, the work would be different, and usually it is. And in this case, it is different. You got negative 5, 6 along one path, and 14, 5, 6 along another path. But if you had a conservative vector field, you would get the same values. Okay, so what I need to show you, of course, is that the sum of two line integrals with respect to x and y is actually equivalent to this idea of work that some force field does in moving the particle along a path. And I will get into that. Let me go back to the ebook here. One moment. I'm going to get into that now. Well, I'll get into that a little bit. Okay, so we have to go to the ebook. Okay, so figure eight has a couple of paths, as you can see. And one path, for the top picture, the top path going from A to B, you start at A and you end up at B. The second path in figure 8, you start at B and end up at A. And so that's like the negative of the first path. So there's and effectively what would happen is if you were to compute a line integral for the first path and then a line integral for the second path, since the second path you're going you're moving along the same path, but you're going the opposite direction. The line integral is reflects that. So for instance, here, the line integral along that path negative c in the second picture equals negative of the line integral of the path c in the first picture. Okay, and it doesn't matter whether the line integral is with respect to x or y. Okay, so that's just sort of a natural thing, and it has to do again with the starting and ending t limits would get switched if you go the opposite direction along the path. Does that make sense? Give me a thumbs up if you're comfortable with that. Does that make good sense? Okay, Noreena's comfortable with that. Wonderful. Okay. Okay. Let's see. I want to show a few more things here from the ebook. Just see here where I'm at here. One moment. Yeah. This is what I want to do next. So we talked about line integrals in two-dimensional space. Okay, but you can have line integrals in three-dimensional space as well. You can have line integrals in three-dimensional space. And the formulas are natural extensions then to the formulas for two-dimensional space. So for instance, if you're doing a line integral with respect to arc length, this would be how you compute that. And they comment that, well, you could just highlight this here. If you look at that integral, you can compactly write that as the integral from a to b. Okay, the line integral can be compactly written as the integral from a to b of the function, okay, at the position vector r of t, which has the components, the parametric equations, x of t, y of t, and z of t, times the length of the derivative vector for r of t. This is section 13.2, Lexi.
Professor, I think that's missing a plus between the dy dt squared and the dz
right.
dt squared.
That's a good catch. Thank you, Lexi. What Lexi's pointing out is the highlighted yellow formula between the dy dt quantity squared and the dz dt quantity squared. They forgot to have a plus sign there. Okay, so they left out a plus sign. You know, just keep that in mind, that there should be a plus sign there. Okay, and thank you, Lexi. Good catch. Good catch. If you have the physical textbook, it has it correct. Now, they mentioned too that for the special case, where your function were equal to a constant, I want to try to have all three things here. Yeah, if your function equals 1, then the line integral with respect to arc length for the function 1 across that curve C, that just equals then the length of the derivative vector from A to B. It's quite fascinating, really. Okay. So you can have, I mean, like if we look at example 5 here, okay, here they want you to evaluate this line integral with respect to arc length, where the space curve C is the circular helix given by those three equations. X is those three parametric equations. X equals cosine of t, y equals sine of t, and z equals t. So you've seen a helix before. And okay, so you just apply the definition and work it out. Okay, so now they do have the plus. All right, so let me see. Yeah, you get the square root of 2 times pi. That's the value of that line integral. And in example 6, they do an example. No, don't do that. Now, hold on. In example 6, they have the sum of 3 line integrals. One with respect to x, one with respect to y, and one with respect to z. Okay, so where C consists of 2 line segments. So example 6, you have the ability now, I mean, if you look at the space curve that consists of these 2 line segments, here it is in figure 10, and they show you that basically what you do is you compute the sum of the line integrals for C1, and then the sum of the line integrals for C2, and then add up the two line integrals. That's what you do. So example 6 is a nice example to look at, and I think you're going to be fine with that. I think you're going to be fine. But let's move on here. I want to try to get 13.2 done. Now here is something about line integrals of vector fields. Okay, line integrals of vector fields. I think what I'm going to do is stop the recording and then do this as a new recording. So one moment.